Okay, example 2, it says, in the beginning there were 400 bacteria in the dish. The number of bacteria increased exponentially. So this word exponentially, let me just point this out. This is the key word in the word problem. It establishes the growth rate as an exponential growth function. You can also do exponential decay, whether it be growth or decay, they're the same. The formula itself is the same. And the formula looks like this. The final amount, let's go with a sub t, equals the initial amount a sub 0 e to the kt power. E is that magical number E we learned about a couple days ago, the base of the natural logarithm, 2.71828182846 ... It's that number that's irrational, it goes on forever, but it's the base of the natural logarithm. K is the growth or decay constant. If K is positive, it's a growth constant. If K is negative, it's a decay constant. Okay? Bacteria grows, radioactive material decays. So that's typically the nature of these problems. Okay, T is the amount of time that elapsed from the initial amount to the final amount. So the initial amount is a sub 0, the final amount is a sub t. When you do these problems, the initial amount is what it is, it doesn't change. The unit of t doesn't matter as long as it stays the same. If this says 3 days later, so t is 3 days, this better ask me about days. Instead of how many bacteria would there be in a year? Well, a year is 365 days, so you'd have to use 365 for your time. So once you've established a unit for time, that unit of time has to stay the same throughout the problem. So what I'm looking at here is there are specifically 2 variables that we're really worried about in this. This is a variable amount, and this is a variable amount. This is a constant that we don't know, and this is going to be a constant that we're going to be told, usually. All right, the typical setup for these problems, they're going to tell you what a sub 0 is. You're going to have to find out what k is. They're also going to tell you a sub t and t at one moment in time. I kind of relate these to direct and inverse variation problems. You had a equals kt to begin with. You had to figure out what k was, and then they tell you something else, right? That's what's going to happen here. This is just the structure for an exponential growth function. So the first thing I want to do after I've established the exponential growth and I've established the structure of my exponential growth, I want to figure out the initial amount, the final amount, and how much time it took for that to happen. All right, so I want to read through the problem and I want to find that specific information. What did I start off with? What did I end up with? And how long did it take? They should give me all that information. So, in the beginning there were 400 bacteria. So the initial amount is 400. That's never going to change for this problem. The beginning amount is 400 forever. All right, that's a constant value, but again, they tell it to us. All right, the number of bacteria increased exponentially. 3 days later, there were 2,000 bacteria. So at the end, there were 2,000 bacteria, and it took exactly 3 days for that to happen. All right, those are the questions you need to ask yourself once you've established. So exponentially creates this structure. Once the structure is created, what do we start with? What do we end with? How long did it take? Once we have those 3 numbers, they go right in those 3 spots. So if I take those numbers, I'm going to get 2,000 equals 400 e to the k times 3. That would be 3k power. And it's kind of set up like the first example was, right? We have something to a power, but the difference here is we got a number in front of that something to a power. We don't want that. We always want the something to a power. So, in other words, the rule says, and I'll use these this time, if I get e to the x equals e to the y, then x equals y. All right? I don't want to have a number in front of my e to the y. So, this number in front here, I don't want that, so I'm going to divide by 400. Even if it doesn't divide nicely, I want to do that. This time it does. 2,000 divided by 400 is k. All right? So again, I'm in a situation here. I want 5, the number on the left-hand side, to have the structure of e to a power. That's what I want, right? So I'm in the same boat I was in example 1. I had 10 to a power. I wanted 17 to be 10 to a power. I've got e to a power. I want 5 to be e to a power. So I need to do the natural log of 5 is going to equal x. Log base e of 5 equals x. My calculator knows the natural log of 5. Hit the ln button this time. and it says natural log of 5 equals 1.6094. So I go back over here, and instead of 5 being e to the x, this is the x, so we know 5 is equal to e to the 1.6094 power. So I'm going to put this right here, e to the 1.6094 power, and that's e to the 3k. E equals e, so power equals power. We divide both sides by 3. So 1.6094 divided by 3 comes out to 0.5365. All right, that didn't answer the question. Okay, all that did was give me the constant of growth. And again, the constant of growth is positive because growth constants are positive. Decay constants are negative. All right. So once I get to that point, again, here's my original structure, right? The two yellow highlighted things are constants, the two blue highlighted things are variable. So the unknown final amount equals the known initial amount, e to the known value of k, 0.5365, times the unknown amount of time. So I convert this structure into a better structure, changing the two specific values that I'm supposed to know into what the specific values are, leaving the two variable values as variable values. And then they're going to ask me one of two things. How long does it take to get a certain amount of bacteria? If you get a number here, it's going to work out pretty much the same way this did. Or they're going to say, how much do we have after this amount of time? In which case, all you have to do is evaluate this thing over here. And that's what they're doing here. It says, how many bacteria, so we're looking for the final amount, would there be in 8 days? Days, units match up, right? So the final amount after 8 days, and it officially a sub 8 if you want to call it that. You can still call it a sub t if you want to, but t equals 8. 400 e to the 0.5365 times 8. Now be careful, this power is all up there, right? So all this stuff is the power of e. So when I type into my calculator, it's going to look like this. 400 times, okay? I'm going to use the second log button. So it's second ln, it gives me e to a power. E caret parentheses. Within the parentheses, I want the entire power. So 0.5365 times 8 in parentheses. And again, it's just a matter of typing in exactly what I see there. 400 is the base times e to the power of 0.5365 times 8 equals, and we get 29,245 bacteria.
Will you be free at the end of this class for 5 minutes?